This is Learning Module 7, I/O Controls with LCD Module, Parallel Communications, and Table Lookup. In this module, we're going to kind of highlight the very important aspects of, number one, how program memory works, and also an LCD module for a parallel interface. We'll go down to the goals. The goals of this module to use a parallel data communication between the microcontroller and other devices such as an LCD module, some of the parallel printers, some of the point of sales type thermal printers use this type of technology. The objective, discuss the need for parallel interface for data communication, explain the structure of data transmission protocol, use short and long table implementations for parallel data communication, and distinguish the limits and uses of the short and long table processes. Controls the LCD module using parallel interfacing, and go ahead and apply short and long table code in the LCD message displaying exercises. We will really have to take a close look at how our program memory is made up in the PIC microcontroller and how you must address using it properly. You'll see here that from the evolution from the Intel 8080, there's always been a program counter. The program counter always contains the address of the next fetch. However, in the PIC, the address is 13 bits wide, and yet you only have direct access to what's called the PCL, or program counter low. The upper 5 bits is called P class, that's these, and they're indirectly accessible via the P class register. Now, the P class stands for Program Counter Latch. It's kind of a holding bin for the upper bits, and you have to address that just a little bit differently than you do the lower 8 bits of the program counter. It is directly readable and writable via the PCL register, and we'll see how we can utilize that. You probably were kind of surprised to see in the instruction set an instruction called return, or RETLW. Well, that's going to be very important for us in controlling something like an LCD display or thermal printer, something of that nature. The P-clave, the latch, the upper bits are not directly readable or writable. You must go through the special function register or the P-class register. It will copy the contents, and we need to preload that before we do any jumping around the various pages. We're going to take a look at the short lookup table routines, and it's a little bit novel in the way that it does operate, but you can see that we simply come to a routine with a certain offset, and we add the offset to the program counter. If you recall, the program counter is, when you power up, it's set to 0. And after each instruction fetch, it is incremented. Okay? So it always contains the address of the next executable instruction. It's often changed when you call a subroutine of that nature, and it's something that you have to be aware of if you're going between pages of of memory. We saw in the first part there that the lower 8 bits will only give us 256 address locations, including 0. But you can see here we come here with an offset, and then we just simply return from it, depending upon what ASCII code or what you want to send to the LCD. We will see that the LCD for the data display register to actually display things, it needs ASCII code. So we'll continue on. Various times you also like to have an end of table marker. I often use FF. Here they've used 00. That's fine, but you need to have the end of table, because what would happen if you accidentally called this and your number for your offset was too large, you would end up way down in the program somewhere else, and the program would crash in nanoseconds. And again, in red, remember that the program counter always has the address of the next program line to be executed, not the one that is currently being executed. The offset value pointing to the desired data location is this typical little thing here where you just add an offset and then you return with whatever data you need. Here's some examples. Also note that if you don't want to have the ASCII number in there, that you can just put the letters into between little marks here, colons, and not colons, they're little markers here, and it will automatically do the conversion for you to the ASCII code. You can also use, if you take a look at the assembly language statements, you can also use a data table. It will do the same thing for you. Here's the ASCII codes, but any way that you use this, when it's disassembled, it will be in the original form of this. Now, liquid crystal displays are pretty unique. Let me show you these. They come in a lot of different sizes and shapes. With the smartphone and the cell phone revolution, they become very popular, even with graphics and other things. But they're all very similar in nature. Even if it's a graphics LCD display, it has data communication lines. Generally, it has a lot more memory where you can control each pixel. Most of the general ones like we're going to use already come with a character set built in, and they relate the ASCII character or the ASCII code to the character that it does. But you'll see that the other things are very, very similar. Now, one thing I wanted to note was that once you get an LCD on your board connected, now you have a viewport on what's going on inside the chip for debugging purposes, rather than just flash an LED if you made it to a certain subroutine or whatever. Now you can actually look at values of stuff. It's one of the first experiments I do with the class, so that we now have a viewport that we're able to get to very quickly. The LCD typically comes, doesn't matter, multiple lines, but generally you have a data bus of some type. We'll see that you can communicate with the LCD with a byte. You can also communicate with the LCD and most of the LCDs with a nibble, 4 bits. They generally have power connections. They often have contrast connections that would go to a potentiometer where you could take and get the contrast just perfect for your application. What's important is that they also have two control lines. One of them is register select, the other one is enable. The register select, if it's low, you're communicating with the instruction register of the LCD. If you want to communicate to the data display, you have to have register select high. And you do have to initialize the LCD before you use it. Here's a typical protocol. It's often suggested by the manufacturer. You can't use the LCD until you've initialized it to be what you want it to be. So that's the first part. Another thing to consider is our trainers have a 20 megahertz crystal or resonator on them, which means they're operating an instruction cycle time of about 200 nanoseconds. Well, you've got to consider that when you power up these LCD displays, you've got to give a little bit of time delay before you try to initialize it. We'll see that ours are about 1.64 milliseconds to clear the display, to let it boot up, or to take the cursor home. But most other instructions where we're dealing with the initialization or we're dealing with the data display are only around 400 or 40 microseconds. But you do have to let the LCD come up to speed. You can put a little 5 millisecond delay before you initialize it. Otherwise, it won't be initialized properly. Here's some more of the commands that you can give it. Clear the display. You can home it. You can go right or left. You can turn on the cursor. You can blink the cursor. You also can have to initialize it whether you want 8-bit transfer or 4-bit transfer. Now you can see here with 8-bit transfer, we're tying up 8, 9, 10 of our data lines. Well, on our some of the smaller controllers, you don't have that many data lines. Here's the initialization sequence that you have to give to it. And remember that when you're going to the data display register with your register select high, it wants the ASCII code. If you do the 4-bit communication, notice you only take up 6 data lines or 6 I/O lines of your PIC. Most of my LCD experiments, we go ahead and do the 4-bit communication so that we have plenty of other I/O for other things like stepper motors and things of that nature. There's also a certain protocol. Here's some supplemental data. Here's a long table routine. Now, on the long table, when you're bridging the different pages of memory, you've got to be concerned with this. And you have to preload your PCLAF before you go to a place on another page. These examples kind of show how you would have to do that and take care of that type of operation. You usually increment your PCL, your program counter low. If you get a rollover in that byte, you've got to be sure that you bump your PCLAF. And remember, you have to do that via using the special function register PCLAF. Of course, some important stuff in red. It's mandatory that when the PC gets modified, all 13 bits get modified at the same time. And after this little routine, you'll see that everything should continue as a normal operation. You can check this out in the simulator if you want to. Here's some more implementation of control, different things you can do with the LCD, and experiment around. This looks like something that would come out of a manufacturer's data sheet. But notice the clear display and the cursor home, 1.64 milliseconds. That's a credible long period of time when you're operating with 20 megahertz crystal, where your clock time or your instruction time is 200 nanoseconds. Again, here's some of the little bits inside some of the control register where you can do a lot of different things. Here's your connection for our particular one that came with the trainer. You can see that we have I/O data bits. One thing, I don't think anybody's ever read from the LCD display. Normally we just strap that such that it's always in the write mode. I think we've done that on, I think you have to do that as shown in the wire connections. Here's some routines to aid you in your logic and your software. There's also some sample routines to get you started. Again, these are important when you're thinking about the logic of what you need and where you need to make decision making. Here's the long table. Here's where you really have to watch what you're doing and keeping track of the peak lathe. Here's some examples that you can try. And again, if you find any errors in this module, please let us know. We're continually updating these and we've made tons of changes. But this shows you how you can look at it in the simulator if you want to study it a little bit further. Okay, well, I hope you like this. I hope it helped. And of course, all our trainers will be available to help you any way we can. Also on the Moodle, keep an eye out. We do have some advanced labs and stuff that we'll be putting out from time to time. Thank you very much.